Alright, welcome back to Forces, Chapter 10. A force is a type of vector. So it's a vector quantity, much like displacement was, much like velocity, acceleration. A force is a push or a pull. Okay? So you're either pushing on an object, you're pulling on an object, something is doing this. There's lots of things that can do that. Forces stretch rubber bands, they open doors, they drive gears, they carry your books. All these things that happen in our life all the time is basically exerting forces. Okay? A force is what causes an object to move or change direction. So in other words, forces cause acceleration. So things don't really accelerate on their own. An external force has to be applied, and that force causes things to move. And that really is the essence of Newton's first law. Objects in motion tend to stay in motion. Objects in rest tend to stay at that rest until acted upon by an outside force. Okay? So you won't accelerate, you won't move, really, unless a force is acted upon you. You got to pick up those books and carry them to your next class. You got to carry your backpack around. You got to open a door. All these things don't happen unless someone shows up and does it. You got to act upon things. You got to have a force. Okay. Now recall that acceleration is how a velocity vector is changing. So earlier we studied distance equals rate times time. We looked at velocity, acceleration, position, all these types of things. And now we're learning that the cause of all that movement is forces. Okay? So forces cause acceleration. Acceleration is a change in your velocity. Velocity is how fast you're moving away and in what direction you're moving away from some reference point. So that's a lot of vectors, right? So let's talk about vector addition one more time. So vectors moving in the same direction is one possible scenario we have. We have vectors moving in opposite directions, or acting in opposite directions. And we have vectors that are going in two different directions. So one of them's going west, one of them's going north, for instance. Okay. So adding vectors, when the forces are in the same direction, it's pretty straightforward. The two arrows combine to create one giant arrow. Some tips are that you need to have your vectors tip to tail. This is always true. Tip to tail is very, very important. Does get a little tricky on the next one, you'll see. But we need tip to tail. If you're going in the same direction, you simply just add them together, make a big vector representing the two quantities you combined, and you're good. If you're going in an opposite direction, you're essentially subtracting each other. So vectors still go tip to tail. Notice that I put them kind of separate so I could actually see one of them is on top, one of them's on bottom. If I put them on top of each other, it'd make a very messy picture. It'd be a little bit harder to add, especially those of you who like to write in pen. It's a good time to go back to pencils. So essentially they're just subtracting. We got 39 Newton force going to the right. We got 34 Newton force going to the left. We add them together. Comes out to be a 5 Newton force going to the right. This is, you're pushing on the table, I'm pushing on the table, and one of us is getting moved. Okay? One of us is pushing harder than the other. Now in 2 dimensions. So this example is actually displacement. You're in kilometers here. But swap the kilometers for newtons, and you'd have the exact kind of concept that you would use. Okay? So still again, vectors line up tip to tail. You make a right triangle, and you're going to solve that with a squared plus b squared equals c squared. So in this case, this is actually displacement that you're looking at here. So this one went 11 kilometers north, 11 kilometers east, and so the resultant was a 15.6 kilometer resultant in a northeast direction. Okay. If I were doing this with forces, this would be a forces pushing it north and forces pushing it east. The result is that the object is moving to the side, northeast, at 14.6 newtons of force. So that's going to determine how much acceleration this object has. Adding force vectors, quick summary. So let's say you got two 5s going in the same direction. You combine them together. Two 5s going in the opposite direction. They negate. Okay? 5 plus 10 going in the same direction becomes 15. 5 minus 10 is a negative 5, etc., etc. We can go up and down, left and right, whatever we want. Basically just adding and subtracting. When the net force is 0, so when the two vectors add together and they cancel each other out, we call the forces balanced. Nothing's really happening. Okay. This is the case for an object acting under gravity sitting on a table, for instance. So the table's pushing up, making sure it doesn't fall through. Gravity's pushing down, making sure it doesn't fly up. And the two forces basically cancel. The object just sits there. When the forces are not 0, the object has an unbalanced force, and that will cause an acceleration in whatever direction it is that it's being pushed. Now, to sum all these up, we have what's called a free body diagram. So in a free body diagram, you draw whatever object it is as a square or circle to make it really nice and easy. We're physicists, not artists, so we don't want to create this beautiful rendering of whatever it is we're moving. We just want something quick and easy so we can go. Okay. Forces are shown as coming from the center of the object and going in some direction. Okay. So here you have an object with 4 forces acting on it. Okay. One of them is gravity, so gravity's holding it down. There's something called a normal force, which is equal to an opposite of gravity. Basically, the normal force is the force that exists that shows that you're not falling through the ground. Okay, gravity's pushing you down, but the Earth keeps you up. Right? Of course, you have some force that's being applied. That's that force APP. And then whenever you try to move, you have what's called friction, which holds you back. Okay? And so all 4 of these forces are acting upon the object all at once. And if you added those together, you could find out what the resultant force was. Okay? It's basically a shorthand notation for summing up a bunch of vectors. If the forces all cancel, the object will not accelerate once again. So balanced forces do not result in acceleration. If the forces are imbalanced, the object will accelerate in whatever direction it is that's left over. So you can see with all these arrows, you're basically just canceling them out using vector addition. Seeing what's left, that's the direction the object moves in. Okay? So what are the forces that you could see in a free body diagram? One of them obviously was friction. Friction is a force that acts in opposite direction to movement. Okay, so if I'm trying to push a box in one direction, friction's going to want to stop it from moving. Okay, so friction is a force that opposes movement. Happens when two surfaces rub against each other. Okay, so friction depends on what type of surface is involved and how hard the surfaces push together. Okay, so for instance, if I put out some sandpaper and I rolled a car over it versus a flat, nice, smooth surface and I rolled a car over it, which one would go further? Okay, if I made the car heavier and I was pushing down more, which one would go further, right? Who's going to experience more friction? So how hard the surfaces touch and what type of surfaces are involved. And there's a few types of forces. There's static friction. It's the friction when you're not moving. Fluid friction, rolling friction, sliding friction. A lot of these are in the Quizlet. So if you go over there, you can look up all those definitions. And remember, you need to be playing that Quizlet game by Friday to get full credit. Gravity is another common force that we show in a free body diagram. The forces on this person are balanced because the floor is pushing upwards, gravity's pulling downwards. Talked about that a couple times in this video. So gravity is a force that pulls objects closer together. It increases with greater mass. That's why you see planets exerting gravity while people do not really. Decreases with distance. So the farther away you are from Earth, the less gravity Earth exerts upon you. The farther away you are from the Sun, the less gravity the Sun exerts upon you. Your mass, greater mass, increases it, distance decreases it. Weight equals mass times acceleration due to gravity. Okay, so on the Earth's surface, that's negative 9.8 meters per second squared. It's negative because it's downwards. Okay. Motion with gravity. A few options here. You got free fall. So in free fall, the only force acting on an object is gravity. It's just falling through the air. There's nothing pushing on it. There's no air probably. You're probably in a vacuum to truly be free falling. Because air resistance creates a frictional force on an object that's going to resist the motion. The more surface area an object has, for instance, leaves and papers and things that have lots of surface area, the more air resistance they'll experience, because the more air will be able to push up and oppose the motion. And of course, there's also projectile motion, which is motion in two directions. Even tossing a baseball or rock or catapult toss or rockets, whatever it is that you're doing here, you're ultimately moving, and you're launching it, you're throwing it, and as you throw it, gravity's pulling it down. Okay, pulling it back to Earth. A lot of those are modeled with parabolas. You're also going to have elastic forces. Okay, one of these is compression. It's where you're squeezing matter together. Think about the free body diagram of a person sitting on a couch. You're kind of squishing a couch cushion there. Whereas tension is the elastic force that stretches or pulls, for instance, fishing line or rope. So a box, very, very typical physics problem is you got a box and there's some sorts of pulleys, and those pulleys have ropes. Okay, box could be at an angle, box could be going up and down, whatever, but there's a box with a rope, and that rope would have a tension. Okay, so the box isn't falling because the tension on the rope keeps it from falling down despite gravity. Okay. In summary, forces are vectors. Okay. Vector addition, pretty inescapable for physics. You'll even see vectors when we come up against buoyancy and motion fluids in about a week here. So if all the vectors cancel out, the forces are balanced, so it's not accelerating. Okay. If the vectors don't cancel out, then an object will accelerate in the direction of the resultant force. Okay. So if there's multiple things pushing and pulling and pressing, yada yada, whatever the resultant of all those forces is in your free body diagram, that's the direction I'm going to move with whatever force is left after everything cancels. Best way to show this is with the free body diagram, because there's a lot of different forces acting on a single object. So you got friction, gravity, tension, all this different stuff happening at once. You figure out the net force, and you figure out what direction this thing's actually going to accelerate in. That's pretty much it for this particular topic. So hopefully you're studying the Quizlet, you're coming to class and doing the labs, and let me know if you need any help. Have a good week, and I'll talk to you in class.